Thanks for coming. So this week we have Jaehoon Kim. We'll talk about Ramsey things. Okay, please.
So, yeah, this is joint work with John Haselgrave and Joseph Hyde and someone. Okay. Yeah, Hong Liu, you know, I mean him, everyone, right? So this is the definition of Ramsey number. So for two graphs f and h, we can define the minimum integer n, such that if you have n vertex graph, it either contains a copy of f or its complement contains h. So usually you, state this as a complete graph and you give a color, red color or blue color. You can consider red color as X and blue color as non-X, then this is equivalent. And this provides, complicated theory, and then determining this number is, notoriously difficult. For example, for the most, basic case or most natural case of considering the complete graph and complete graph with the same size, we have this big exponential gap. So lower bound is using robust local lemma, the probability construction, and upper bound is directly varied by Shah, Ashwin Shah, using pseudo randomness. Wait, one is YK. And so this lower bound construction is probabilistic, meaning that this doesn't give you an explicit example that we can kind of see its like structure. But people have tried to also find the explicit construction. But those are really difficult. So for example, the best one we know is still not exponential. In 2012, they show that this is at least 2 to the log n to the 1 plus epsilon. So this, this is a super polynomial, but not exponential. So then, what kind of explicit construction that gives lower bound that we know? There is this like a very natural, easy lower bound construction that, everyone understands why it's, lower bound construction. So easy construction. Which works for general, f and h. So what we do is, let's say you have f who has number of vertices is small f, and h is a graph which is, k-part type graph, where the smallest part has size say sigma of h, which is the size of smallest part. And what construction we can think is just very easy construction. You take f minus 1 vertex, f minus 1 vertex, f minus 1 vertex, and sigma of h minus 1 vertex, and then put complete graph. Assuming this is smaller than f. You choose so that this one is bigger graph. This one is bigger than h. Then, in here, you cannot find f inside here. This is graph. And then h. So, obviously, this k parts. H, if you want to find the complement, h in the complement is complete multi-part type graph. And you have to put these each part to each one of these independent sets. But the smallest one, so smallest one is this means that every part is have size bigger than or equal to this. But here you have a smaller part, so you cannot fit in, any part here. So this provides a lower bound.
You mean h is completely part type?
It doesn't matter, but okay. Chromatic number k.
Chromatic number k.
Yeah. k is the minimum, number that you can do that. And okay, technically, so among all partitions, so let's say this is the minimum among all partitions, to be more precise. For some other partition, it could be large, but one partition, which does that. But the compound this give is that the only polynomial bound. Meaning that in this case, if you consider this kn, that give you just this side is n-1 times n-1 you get. So which is only polynomial. So this is, in general, very poor bound. Then, since this Ramsey number for general graphs are extremely difficult, what we can ask is that because this doesn't give you a good construction, then we can naturally ask that if we change the graph, then can you make this as a good bound? So natural question is then for which graph? The above construction or bound is tight. So this is a very natural question because problem is too difficult, so we cannot do anything. Then we have to, go the other direction. So how to make it easier? So regarding that, Burr and Erdős, I didn't write down the year, define what's called Ramsey group. Meaning that if some graph pair satisfy this as its optimal construction, then they are good. So in fact, they said F is H good if its Ramsey number is exactly what you get from the above construction. So now the question is, what graph is what good? Of course, from this example of complete graph is never good. If you have complete graph is not complete graph good. Of the same size, at least. So this, and if we have some graph which is quite dense, then intuitively they must be more close to the complete graph, and then which has exponential lower bound here. So probably dense graph is not so good. And probably we can see that we must consider like a sparse graph first. So what's the most natural sparse graph one can think of first? Trees. And among the trees, what's the simplest one? Path. So Erdős show that path is KK. So meaning that if you consider a Ramsey number of complete graph and KK, and that's, this equality holds. And how Gerensor and Gierfash, I'm not quite sure whether my pronunciation is correct or not. If I mispronounce your name, then I'm deeply apologizing. If you are still alive, okay.
Well, this one.
Yep.
MN bigger than K.
Yes, right. Is it K or bigger than K? There is condition, right? So I forgot to write it here. There is condition, yes. Yeah. And then Gerensor and Gierfash show that the Pn is Pk equal. Yeah. And the Bata 1977 proved that every T is KK good. So I think, yeah, I taught this in the introduction to graph theory. Maybe you also taught, I don't know. Yeah. Anyway, in KAIST we learned this, and the argument is not difficult if I wait. Do I remember correctly? Anyway, so this argument is not so difficult.
Incorrectly spelled. So C.
Yeah. But yeah, right. Yeah. Yeah, I'm butchering lots of people's name. In fact, I mean, this concept of Ramsey Goodnick has some connection with lots of graph theoretic notion. For example, I mean, this Vatal proved that in particular this K1D is KK group, right? Okay, that was, yeah, anyway, yeah. And this actually is equivalent with the Turan theorem. It's not difficult to actually show. If you know Turan, then this is, I mean, kind of easy. So this is like existence of vertex of degree D or independent set of size K. Right? This direction is not difficult, and the other direction is also not difficult by, I mean, showing that if you have a graph which doesn't have an independent set of size K, then this guarantees that there is a vertex with a degree at least D. You remove it, and then you repeatedly applying this statement for different D. And you can keep removing each vertex with a degree at least something, at least something, at least something, which give you a bound on the number of edges, so which will contradict Turan. So, I mean, both directions is not difficult.
So you're assuming that D is big, right? The D as a function of K.
I think this one is there. I think it doesn't matter. I didn't write down any bounds here. Maybe, did I forget the bound? Fatal. Where? I mean, on the reference that I used, it just said that every T is KK good without any bound. Okay. Then, now what? We consider the tree. Now, next thing is cycle. I mean, that's natural. So once you, not completely, but this kind of says that for every tree, you can consider, this goodness with a complete graph pair. So next natural thing is to move to cycle. So that also people have considered. Bondi and Eldridge, 1973, so that the Cn is KK good if n is bigger than, say, k square minus 2. And Eldridge, Badri, so they conjectured that Cn is KK good when n is at least K and K is at least 3. And recently, Kibash, Long, Skokan proved that this is true in a strong sense that this n bigger than k is not really necessary. It's more like it could be more small. Of course, for this c, it could be large. So for small number, this might not completely resolve it. But for large number, just this. And in terms of, small k and n, Nikiforov in 2005 proved that n at least 4k plus 2 is enough. Okay. Then, next question is, what if we, just put the complete graph here, or other graph? If we put other graph here, then what result can we get? That is this theorem by Burr, 1981, which said that Cn is H good for general graph H if n is sufficiently large compared to the number of vertices in H. So, that sufficiently large is some tower type function. So roughly what Burr did is maybe, yeah. So what we want to show? We want to show that the Ramsey number of Cn H is n minus 1 chi minus 1 plus sigma of H. This is what we want to show. Roughly, Burr's proof is something like, on induction, so that you assume some lower case and then find say either Cn minus 1 as an H, or you have a H minus 1 independent set. So chromatic number goes down. So you can use induction so that if you have this many number of vertices, you can find both of them in here as disjointly. And then what you do, what Burr did is that if there is some vertex which sends lead here, then you are done because you have a longer cycle. And also if some vertex here which sends lots of lead edges to here, not conjectively, and what we can also see is that this must be blue, because if that's lead, if this one was lead, then what you do is you go, you come and then you come here and then go curve. You can complete your cycle in this way. If this one was lead, then that gives you a cycle of one longer, value. So this is blue. By the same logic, this is blue, this is blue, this is blue, and you get a blue complete graph. So which, if this n is much larger than here, then here you already find H, you are done. In other case, what's the remaining case? Every vertex here sends very small number of lead. Then most of them are blue, so you find one independent set here, and then which can play the role of I, and then you attach, you are done. So roughly in this way, but these kind of argument parts, n has to be bigger than the square of number of vertices here. But due to you have to apply induction, it kind of goes to as a tower type function depending on the this chromatic number. So you have a tower type function with a height same as a chromatic number or something related to chromatic number. Anyway, the question is that can you get a better relation between this N and this H? In fact, there is this conjecture by Allen-Brightwell-Skokan, 2013, that if N is bigger than chromatic number of H times the number of H, then Cn is H good. So that was conjecture. So if you think about this problem, so in order to prove this equality, the lower bound is already given. So we only care about the upper bound. And if we consider a supergraph of H, and then if we find the supergraph of H, then it naturally gives you a subgraph H. So we only need to prove upper bound. So we can assume that adding some H to H and then prove an upper bound, then that gives you the desired upper bound as well. So we can assume that H is complete bipartite, complete k-partite, complete multipartite. So let's say K of M1, M2 to MK, where M1, M2, MK are in order. So M1 is the smallest one. M1 is the sigma of H. With that, recently, Okrovsky and Sudakov proved that if H is bigger than the chromatic number of H to the 23, and N is only bigger than MK, if we know that H satisfies this, then this is true. Cn is H good. So for many general H, they prove this. In fact, more precisely, this MK being bigger than the chromatic number to the 22 is enough. So which means that if H has its chromatic number smaller than its number of vertices to the 1 over 23, so polynomially smaller chromatic number, then this is true. But this is, you can see this as a, but the bound here is even weaker than what they conjectured. It could be, as small as the size of H. But you have this additional condition. Recall that for almost all graph H, its chromatic number is, its number of vertices divided by log of this. So, you can also see this as a strong condition, but this bound is much better. So this is what we know. And what we prove maybe I should, anyway. So what we prove is that this conjecture that I just deleted is true. So if n is bigger than some constant times the number of vertices of H times log to the chromatic number, then we prove that Cn is H cube. So what's written here was that when n is bigger than H times the chromatic number, that was conjectured here. Here we said that H times logarithm of the chromatic number. So in some sense, I mean, it's we proved the conjecture in a stronger sense. But of course, we have a constant C in front. So it doesn't answer that for a smaller value of, I mean, the number of vertices in H and chromatic number H. So this bound, this lower bound, and is something like 10 to the 10, maybe 10 to the 20, something around that magnitude. So this lower bound is tied up to this logarithmic term. Because if you consider H looking this way, say here you have like n. So completely multiply type graph that one part is size n and rest of them is small, let's say s. Then Cn is the cycle. Then if you consider just n-1 click, and there are k of them, then this one has more vertices than the above, because the last one in the natural construction, last one was smaller, the size of S. The last one was the sigma of H, but here we don't care. Then in that case, Cn does not fit into any one of them. And then H also does not fit to any one of them, not because of this, but this big part has nowhere to go. But this has a number of edges in here is strictly bigger than where is the expression that? Yes. So this shows that in this case, I mean, this Cn is not H good. And if you see, then this is n vertices, and H has, these are small, and this also has around n vertices. So, I mean, if you remove this, it might be still true, but you cannot go below. So n has to be at least linear in terms of the number of vertices in H. So, let's.
Do you think that the linear lower bound can be seen now?
Probably, yeah. Yeah, probably. But our proof methods use some sublinear extender, so it's, I mean, for our proof method, log term is kind of necessary. But I mean, probably, yeah, it's linear bound might be enough. So basically, roughly what we want to do is induction on K. And for that, Pokrovsky and Sudakov already proved for K equal 2 case. Exactly. I mean, with some bound. So this is actually this with the, yeah, if n is bigger than some constant times n2. So in fact, their theorem, already you know this exactly for K equal 2, which is big bound. And by assuming that, we want to do roughly this. M1 is smaller. Yeah. So what we want to do is we want to use the following construction, which was used by Liu and Montgomery in recent breakthrough paper that they write. So we want to take some O cycle. And you take almost antipodal points, meaning that one has length L, one has length L plus 1, and then connect. And then here you take a long cycle, which has length L less than. So one of the difficulties here is that when we want to find cycle, if we just want to find a cycle with a length longer than something or smaller than something, well, that kind of thing is not too difficult, but you want to make it exactly n. That's one of the difficult parts. So what we want to do is we want to find this kind of structure, so that this one is, say, C, first one. So let's say A1, A2 to say A2mk. And let's say number of vertices in M is mk. So average part size is M. And then there are k parts. Let's say you want to, so what we want to do is we want to build this. Once we have this, then what we know is that we are assuming we have a, where is the number? Yeah, I didn't write. So k minus 1 times m minus 1 plus sigma of h. We want to assume that we have a graph with that many vertices, which doesn't contain h in its complement and which doesn't contain cn in its graph. So assuming that such a thing exists. So this is this doesn't contain h in its complement. That means if you take set mk vertices here, and then we take m1, m2, m3, mk. Then if there is no h's between them, then in each complement you have a h. So there must be an h. Then you can shorten this cycle by the amount less than mk. So you can keep do this until the cycle length here. Let's say you take always the longer part, and then you measure the cycle length, and then you do that until that length is between n and n plus mk. Some number between here. Until that, you can keep shortening it. And then once you are in this range, now you change long path to short path. Then this decreases by 1. And you change again until you hit exactly n. So that's roughly we want to do. For that, we have to build this. And then how do we want to build that? We want to use some expansion. So we want to use expander. Expander is a graph that if you have a subset, then it extends lots of edges outside. I mean, more precisely, it has lots of neighbor vertex outside. And if you have an expander, we don't know whether our graph is expander or not yet, but if you have an expander, then in here, I mean, it's not difficult to it's not difficult to find the short order cycle, because if everything is bipartite, then I mean, it's becomes easier. So you take a short cycle, and then you take a short cycle, and because it's expander, you take it's a neighborhood, and it gets bigger, and again it gets bigger. Big set, you just take a neighborhood, keep taking neighborhood until both sets have size bigger than half, and there must be an intersection. So that provides this path. While you're doing that, because this is big, anything much smaller than that you can kind of avoid. So you can connect this while avoiding some small set. and you connect this while avoiding previously built part. You connect this while avoiding previously built part. You can keep do that until you get some this structure. And I mean that's roughly how we can get one adjuster. Let's say this is adjuster. But roughly, I mean, this is, I mean, by doing that, we cannot get, I mean, exactly to this adjusting power. So we have to do a bit more. But that gives you some idea on why we need this expander. Where did I left eraser? Oh, yeah. So this kind of justifies that we need to find some expander inside the graph, right? Now what we can show is that we can actually find the expander. Because what we can do is if the graph is not expander, we want to take into subgraph, which is expander. But it must have still some good property that its complement is H3. That's kind of obvious, but we want a bit more. So what I mean is that if you have H, which looks this way, then what you can do is if you have G is our graph, and then which is, I mean, say, satisfy certain inequality. So whatever M is, I mean, we can find some M satisfying this equality. Because G itself, we know how many, G is the entire graph, so we know how many vertices are there. And then N is large. So this is certainly much bigger than this. So this number, you can just put large number here. And what does it mean by this is not expander? Then you can divide the graph into two parts, here and here. And then it has only small neighborhood. And then there is no edge between here and here. So if the graph is expander, then we are good. We already found one. Otherwise, we have this structure. Then what we do is that we can divide this into two parts. So this is K1 part, K2 part, so that this part has size bigger than M times, let's say this part is H1, this part is H2, H1 log K1, this has size bigger than M times log H2, H2 log K2. We can do this because summation of these two is quite smaller than this. The other part is kind of same. H1 plus H2 is H. But the log, I mean, so naively thinking, log K and log K over 2 is like, this is log K minus 1, right? So what you can actually see is that if you have M times H1 plus H2 log K here, and this is actually, I mean, MH1 log K1 plus MH2 log K2 plus some additional term we can get, depending on, this is computation. Additional term, which is roughly 1 over log fraction of the thing, which is like, this may not be entirely correct, but something like this term without log. So if your expansion is strong, that this small part is smaller than this, then by adjusting K1 and K2 accordingly, we can show that this one is not so small and this one is not so small. And because there is no H between, we know that either this one is H1 free in its complement, or this one is H2 free in its complement. So you can shrink your graph into subgraph, whose complement is also some graph free, and you repeat it until you get the expander. I mean, you cannot do it too much time. The K is bounded. So at some point, you must have an expander. I mean, without the technical detail, because of that, we can get some expander. But as I mentioned, in order to get this large adjuster, I mean, having this one is not enough. This, I mean, you can do this, but you will get a problem at some point if it gets too big. Too big, but not as big as we want. So what we can prove is that where is it? So what we can prove is that if in addition any two large sets can be connected by many passes. So if we can assume one more thing, that if any two large sets can be connected by many passes, then what we can prove is that if G, that is, let's say G prime is the expander that we pass on to. If this one has at least, say, 1.9n, then we can find the Cn. And if this one is at least 0.9n, then there exists the long adjuster of length at least 0.7n. By the way, I mean, I think I didn't mention, so lots of proof idea that we use come from the Pokrovsky-Sudakov paper, and also Kibash, Long, and Skokan's paper. And this kind of, I mean, big picture is quite similar to what Pokrovsky and Sudakov did. But there, I mean, they use the polynomially many passes, but we improved to the logarithmically many passes. So why is this? So as I mentioned, we can build this kind of structure, but we are not sure whether we can make it long enough, right? So what we can do is we can keep taking this structure in a disjoint way. And then if we know that there are many passes between any two large sets, and we can find many two passes between. Since there are many two passes, we can, by using some, not pigeonhole, but some basic Ramsey, we can find the two passes where distance between this is not so far, and this is not so far. Then you can just merge this by deleting this, and you get a longer adjuster. And then you keep do that. Yes. Yeah. I mean, that's no problem. You just delete this, and then in the remaining, you find another expander using your lemma. There you find, and you delete, and then you have a graph, you find another. I mean, you keep applying that lemma. So whatever graph you remain, as long as this is constant fraction, you can find another expander inside. And then there you can find this adjuster. The problem was just connecting. To make it long was the difficult. But if we have this additional condition, then you can find many passes and choose to connect. You can keep do this while losing small fraction. So numbers match out, so you can find. So in the above case, if there is enough room, then we can be done by finding cycle. But the graph could have less than n vertices, right? Because you don't know when you stop. But as long as this is at least 0.9n, then you can find the adjuster of the length, like more than half. So now with this, we can prove stability. How? You have G, and I mean, roughly speaking, if this doesn't happen, then by Mangal theorem, your connectivity is low. So you can take a cut set and then you delete. And it splits. And then again, in each graph, if that doesn't satisfy, then you take a cut set and then split. Then you keep taking a cut set, and then that can be done at most k times, because if you take a cut set and then there are k parts, and if each of them has a size bigger than m1, then you already find h here, because there is empty, empty, empty. In its complement, it's a complete multiple type, complete multiple type. So if you get k components, you are done. I mean, essentially, you don't care about two small components, but if you get k component, you are done. So by collecting this cut set, this has size at most k times log 4 k. And then you can get these joint sets, which say, what's the good letter? Why did I write H here? H is not good. A1, A2, A3, AS. And F is at most k minus 1. Oh, that's not A then. E? So this is a graph that graph G, you can decompose it this way. And what do we know is that if one of them is bigger than 1.9n, then we are kind of done, because I mean this satisfies, you cannot do this anymore. That means that it satisfies this additional condition. And then we roughly, I mean, there is the issue of like when you take the lemma and what's the graph you are working on. But if essentially, I mean, if this one has more than 1.9n, you are already done by finding Cn. So we know that all of them has size smaller than 1.9n. And what we know is that, did I also erase? So Pokrovsky Suvakov says that, I mean, R, C, N, K, M1, M2 is N plus M1 minus 1. So if one of them has size bigger than N plus M1, M1 is small, so let's say 1 plus epsilon N, then that must contain this in its complement. Otherwise, we get a length of size n, right? If something is bigger than that, then you get the two parts which are empty here. And give me a moment. Yes. So that's what we know. So that means that maybe. So from there, what we know is that, how do I explain this? So entire graph has k minus 1 n vertices, roughly, plus something, but it has roughly this many vertices. And if there is a part which has bigger than n vertices, then you can find two parts which can form a H, right? H has k parts. If this one is bigger than 1 plus n, 1 plus epsilon n, then you can find two parts from there, right? But how many parts do you have to find? K parts, right? So you find two parts here, and if this one is smaller than 1 plus epsilon n, then you find just one part, where this and this are completely independent. So this can play the role of one part in H. One part. As long as this is bigger than this, you can find two parts. Then why are finding two parts? So you have to find the you have to find the k additional parts, and then you have this many vertices. By deleting this into k minus 2n, you just lower by, this is n most 1.n. So you lower by n most 1.9n, and you lower this by 2. And then you find one with a size smaller than n. So you take the subtract n, you subtract 1. You keep do that, then you can see that if there is at least one part bigger than this, then we exhaust this part first before this and find the h. That means that shows that none of them has a size bigger than 1 plus epsilon n. Would it be? I think I didn't do a good explanation here. So maybe easy case, let's say k equals 3. K equals 3, you have 2n, this is too easy, okay. K is 4, you have 3n vertices. Roughly 3n vertices. So here, this is only k log 4a k, so you can just forget this. And then if you have 1 plus epsilon n here, then you can find the two parts, m1 and m2, right? And then if here you have n vertices, and here you have n vertices, then you can just find m3, m4, and then that's already h you get, right? So what I'm trying to say is that if there is, but the number of vertices is 3n, so you must have to get 3 parts, right? There is no way that you get 2 parts because it's smaller than 1.9n, it's smaller than 1.9n. So you must get 3 parts where you can find 2, 1, 1, which give you h. Because of this number, you must get 3 parts. So by that argument, you can show that everything here is smaller than 1 plus epsilon n. And then, because we know that the entire number of vertices is k minus 1n, it's actually very close to n, very close to n, very close to n. So that gives you stability.
Claiming that 1.9 times 2 is smaller than 3 and 3?
So you have 1.9 times what?
1.9 times 2 vertices, 2 vertices.
That's bigger than 3n, right? So this is never happening in this simple case.
You mean that every part is smaller than 1.9?
Yes, every part is smaller than 1.9. So what's the worst case? If this one is 1.9n and rest of them is like 1.1n, so then it has to be 1.1n, right? Which is bigger than 1 epsilon. That means you can find 2 parts here, 2 parts here, entirely 4 parts to get h, right? But if this one is 1.0n, then 0.1 has to go somewhere, so you must have a third part, right? Then 1, 1, here, here. That's intuition. I should have written down more computation, but you can compute this to actually show that that holds. So that gives you stability, meaning that now you see that you have this structure, B1, B2, Bk minus 1. Graph looks this way. And each of them has roughly n vertices. But now, again, due to what I deleted, we know that if this one is, we know that this one is at least 0.9n, right? That means we can find the adjuster cycle of length at least 0.7n. And here also adjusting cycle of length at least 0.7n. So if there are two passes we can find. If there is these two passes, and we can merge them, and then now you do what we did later, what we did before. We can, keep reducing the length by mk until it is n cross mk, and then you adjust. So if there is these two paths, then we are done. Otherwise, the entire structure is one connected. It's not even two connected. That means you can find some bi and then one cut vertex. So everything you can kind of do the block decomposition, the maximal two connected graph block, and you can find some parts here. But if you reduce this to one part, then recall that we are doing all the things in terms of induction on K. Induction on K, one good thing is that if you have M1 set, it gives you expansion. Meaning that whatever M1 set you take, its neighborhood, together, this must be at least N. Because if not, you have a M1, and then small neighborhood, and this is smaller than N. And you take this set, and then you delete this. And then in the entire remaining, you apply induction to find the H minus 1 part. Technically M2, sorry, M2. M1 has to be kept as a sigma H. Then this and this are entirely disconnected. So you just add this to H minus this one part to get H, right? So this induction hypothesis says that any M2 set expands to N. That means in this block, if you take M1 set, that expands to N, meaning that here you have a more than, N plus, you can do some computation. You can show that you have more than N plus M1. And then one thing I forgot to mention is that in this stability, each one of them is K, M1, M2, 3 in its complement. Because otherwise you find two sets, and then one set, you are done. So using this and this condition, wait, do we even use that? Yeah, anyway, you use that and this, and we apply the K equal 2 case. The Pokrovsky-Sudakov proved that when K equal 2, in here, if we have this condition, if this one doesn't contain this bipartite graph in its complement, then you find the cycle of length n. So you can find the cycle of length n here. Yeah, I hope, what I said was not too confusing at the later stage. And time is up, so I will finish it here. Thank you.
Thank you very much. Questions?
So, I probably didn't follow all of your sentiments, but one thing I want to ask is, I can believe that you can get some asymptotic time bound by this, but how are you getting the exact bound by using this expander thing?
The eject one was this last argument. That so by using this, you can get there is one part which is only one vertex is connected to other, and then this is the cap. And then using this inductive argument, you can show that this has certain size. And then there just you apply the, K equal 2 case. And then how you prove K equal 2 case is, actually I don't remember. The Pokrovsky prove it in, I think they use some rotation extension within as well, but the proof was not long. I think it was 1 page or something.
Any other question? Is there some reasonable conjecture for more with more colors, like 3 colors?
But how many of them are cycle and how many of them are general? And that's also a question. Right? So in Ramsey, if you make some variation, then all of them are usually very difficult.
Any other questions? So let's thank the speaker.